In today's video, we're going to continue from the notes of last class, starting with this example here. And we're going to graph each stage of the rational function where y is equal to 1 over x is transformed by a horizontal stretch by a factor of 1/4. So let's deal with this horizontal stretch first. So our parent function is the graph 1 over x. So here's some key values of the function 1 over x. So we know what our parent function looks like, or the very basic rational function. So we have two little pieces. We have vertical asymptotes at x equals 0 and a horizontal asymptote at y equals 0. So now let's deal with the first transformation was listed, which is a horizontal stretch of 1/4, or horizontal stretch by a factor of 1/4. So what does this horizontal stretch mean in terms of my function? So if f of x is 1 over x, then we can have this new function g of x, which would be the f function of 4 times x, which translates into the original equation I've worked at 1 over 4 times x would be my function with this transformation. Another way to look at this is you could look at what does this mean in terms of the individual points on the graph. So the point xy, so every xy point on the parent function now becomes the point 1/4 times that x value, but it has the same y value. So I can take each of these x values, times it by 1/4, and then give me the same y value. And I can do this for every point on my parent function in order to get my new transformed graph. Now I've zoomed in a lot on this graph, so it's getting kind of hard to see it. So I'm going to move to technology to help me sketch the graphs after this point. So notice that my vertical asymptote and my horizontal asymptote are still at the same spot, x equals 0 and y equals 0, since 0 times 1/4 is still 0. All right, so let's look at our next step. We've dealt with the parent function. We've graphed the horizontal dilation. Now let's look at this vertical stretch by a factor of 3. So that's going to give me a new function h of x, which is going to be 3 times my last function g of x. And if I look at this in terms of the original equation, I'm up to h of x is equal to the function 3 divided by 4x. In terms of each individual point, the xy value of my last function, g of x, well, now I'm going to multiply each y value by 3. So the x value stays the same, and I'm going to multiply that y value by 3, and it's going to change my transformation of my graph. As you can see, the purple line is now the new graph for step 3. Next, I'm going to deal with my translations. So I'm going to start with this top one, which is my horizontal translation, and then I'm going to do my bottom. So horizontal translation means that I'm going to move this graph. Since it's a -2, that means 2 to the left. So let's say I have the new function p of x. That's going to be my last h of x function. But this time what I'm going to do is I'm going to move 2 to the left. So that becomes h of 2x plus 2. In terms of the points from h of x, so the points of h of x is now going to become the point x minus 2, and then my last y function, comma y. So I have my y function. So I'm going to start by moving my asymptotes, because this is the first one that affects the x and the asymptote. So notice my vertical asymptote, which was at 0, is now at -2. But my horizontal asymptote stays the same at y equals 0. Then I'm going to move every single point exactly 2 to the left, and that transforms my graph into this green graph. And because this is hard to graph on this very small graph here is the green graph with use of technology. Next step, we're going to do our vertical translation. And this has 3, so that tells me it's going to go up 3 units. So I'll call this function q of x, which is my p of x function plus 3. In terms of order pairs, this means that every xy on my p function gets 3 values added to its y function. So my vertical asymptote will stay at where it's at x equals -2, but my horizontal asymptote has now been moved up 3 units. So my graph is moving straight up 3 for all corresponding points. And you will now have the graph, which is this red graph at the very end, is my final graph of this transform function. The order of operations that you perform any transformation can make a difference in your graph. So here's the rule of thumb that you usually follow with order of operations. You start with the parentheses, the most inside function. And the transformations that are usually in the parentheses will be your horizontal dilation and your horizontal shifts or translations. Next, we're going to deal with the multiplication outside the parentheses, and so that is your vertical dilation. Third, the negatives, which translates to our reflections. Fourth, you're going to deal with addition and subtraction outside the function, which is your vertical shift. I'm going to look at a couple examples of how to use this order of operations for transformations with transforming functions. But sometimes the function is not written in transformation form, so sometimes we have to do a little algebra first before we can actually solve the equation. So this is what this next example has to do. It's how we can rewrite this so that we can see the transformations of the function. The IB exam is usually rational functions are the ones that you'll have to rewrite. So that's the example I'm going to use in this problem. Okay, looking at the equation, y equals x plus 2 divided by x minus 3. We're going to rewrite this. So first thing you're going to do is you need to rewrite the numerator so that it has the exact denominator in it. So x plus 2 can be rewritten as x minus 3 plus 5, because that'll simplify down to x plus 2. Now we're going to divide up our rational function to 2 separate fractions. And notice that we always have that denominator, so we're going to get 1 plus 5 over x minus 3. So I can rewrite this in transform form as y equals 5 over x minus 3 plus 1. So this will easily let me identify my transformations. The denominator x minus 3 will identify our horizontal shift. So this tells us we have a horizontal shift 3 units to the right. The 5 will identify our vertical stretch or compression. In this case, it's the vertical stretch by a factor of 5. And the plus 1 is our vertical shift or translation. And this is a vertical shift upward by 1 unit. Do one more example. This time our parent function is the absolute value of x, so f of x is defined by absolute value of x. Now we start with our parentheses or the inside function, and so we're going to deal with that 2 that we're multiplying the inside function by, and that tells us that we're going to have a horizontal compression by a factor of 1/2. Function notation, our new function g of x would be equal to f times 2x. In terms of our points, we can redefine the point xy as the point 1/2 x comma y. So every x value is going to be multiplied by 1/2, and the y value is going to be the same. So for example, in our parent function, we have the point 1, 1. So in my new transform function, I should have the point 1/2 comma 1. Okay, next, still working inside the parentheses, I'm going to find my horizontal translation. So I'm going to set what's inside the parentheses equal to 0 and solve, and that'll give me my transformation left to right. So I'm going to rewrite h of x as our new function, which is our last function, g of x, as g of x minus a negative 1/2, which becomes g of x plus 1/2. Now this means that for every point in h of x, I'm going to subtract 1/2 from each x value. See on this graph, my green graph, which was my last g of x function, I subtract 1/2 from each x value to get the green graph. So let's look at the point 1, 2. Now notice it's moved over to the point 1/2, 2. So I've subtracted a half from my last x value. And this happens on every point on the g function's graph to get my new transform function h of x. Our next transformation is the dilation of the 2. So I'm going to take my last function, h of x, and multiply it by 2 to get p of x. And this tells me I'm going to multiply each of my y values by 2. So the x values will stay the same in my blue graph, but the y values will be multiplied by 2 to form this new red graph. And this is our transformation. Next, we're going to deal with the reflection, or the negative. And so q of x is going to be equal to negative of p of x, which is a reflection in the x-axis. When you reflection in the y-axis. When you reflect in the y-axis, your y variables become the opposite. So a reflection in the y-axis is the same thing as a reflection across the x-axis. And so I have all the same x points and just switch my y values. My last transformation is this negative 2, which is a vertical shift 2 units downward. I'm going to call this function r of x. So that's going to be my q of x minus 2. And that translates from my r of x function. Each point I will subtract 2 from the y value. And this moves my function down 2 units. As you can see, the purple graph has now been moved straight down to this yellow-orange type graph, and that would be my transformation and my final answer to the graph of this function.